Okay, now we're talking about potential energy of a spring. Remember, you can use U for potential energy. You'll also see that written, so be careful with it. The key thing to understand, it's a linear graph. What that means essentially is the force varies. It is not constant, where quite often we have encountered forces that were the same. This is a force that's gonna vary. Now, first of all, anytime I see a graph, again, I want to think, what does the slope tell me? What does the area tell me? The slope for this case is going to be f over x, which is k. Again, the negative sign really is only there to indicate direction. And the area under the curve is going to equal f times x, which is work. And that's kind of what I want to play with right now, because one of the key things about, if I do work, I give an object energy. So we will use work and energy almost interchangeably. Work is when you're physically doing it. Energy, it can be stored. Well, when we're talking springs, then we can talk about stored energy. Now, so I can essentially say this: work is equal to the change in energy for an object. That'll get its own treatment later, because that's kind of important in the physics world. But let's go take a look at this real quick. Well, we also know that work is equal to force times displacement. But since we're talking about springs, it probably makes more sense to say F times x, because when I compress a spring like this, the distance it changes is going to be x. So if I have a spring, it has a certain initial length, x1, and then I stretch it, I now have a new x value. It's this number that's really important. This is my delta x. So if you want to write it as f delta x, you can. I'm okay with that. Now, there's two ways to think about this. And I'm going to say, when I do work on a spring, I'm going to give it potential energy. So this is elastic potential energy or spring potential energy. And what I want to do is calculate what that is. Now, if I go up to my graph here and remember that work is equal to force times displacement, I can simply say that area is going to equal F times x. Well, now when I take a look at this is a triangle, so it's going to be 1/2 the base, which is x, times the height, which is f, and it's 1/2. So now, but I don't want f in there. I want to replace f with what it was before. I'm going to say 1/2 x, and f, we know from Hooke's law, is equal to k times x. There's a negative in there, but we don't really have to fool with it here. Is going to be k times x. If I reduce that, I get 1/2 kx squared. And that's equal to PE of a spring. And that's kind of important. So if I know how much the spring is compressed, I can calculate how much area it has. The other way I can do it is come back up to my original graph here, and remember, work is equal to F. Let's go ahead and write x, Fx, since that's what we did earlier. But here, this is not a linear force. But if this is my starting point, excuse me, my ending point, and that's my starting point, my average is right there in the middle. Well, the average of two numbers is going to be that number divided by 2. So what I'm going to say is 1/2 of the force times x, and of course the force is kx, so I get 1/2 kx squared again. What it essentially means is this area under the graph here is the same as that area there. Those would be the same area when we do it. One's a triangle, one's a rectangle, but they would be the same thing. Okay, let's take a look at an example with this. And let's only look at one example at a time. Let's cover that one up. So a spring stores 20 joules of energy when compressed 5 centimeters. How much energy is stored when the spring is compressed 15 centimeters? So what I'm looking for is the spring energy. and the new spring energy is what I'm looking for. Now, here's the key thing in this. You don't actually have to know K to solve this, because we know that U of a spring is equal to 1/2 kx squared. Well, I knew before that I had 20 joules when x is equal to 5 centimeters. So what I want to know is what happens now when x is equal to 15 centimeters. Here's the key thing. I know the spring constant is, wait for it, constant. So therefore, when I say 1/2 kx squared, that's not going to change. So I'm going to have 1/2 k, and what I'm doing is tripling x, and that's squared. So I get 1/2 times 9 squared. So what happens essentially is this thing changed by 9 times, because 3 squared. I got carried away there for a second, math-wise, English-wise. So therefore, since U spring, went up by a factor of 9 times, this is 180 joules. It's 9 times more than it was before. You've tripled the x, and since it depends upon x squared, it's gone up by a factor of 9. Okay, let's take a look at another one. A 200-gram mass stretches a spring 40 centimeters. How much energy is stored in the spring? Now, so in this case, I'm going to say U of the spring is equal to 1/2 kx squared. In this case, I need to know k. So let's go ahead and solve for k. F is equal to negative kx, and again, the negative sign's only really there for direction. And by the way, if one of these is negative, well, if x is negative, you put over here, it becomes a positive value because you're squaring it. So that alone gives you the right to fool or to quit. Not worry about it, excuse me. Can't talk today. So k is equal to F over x. 200 grams is 2 newtons. Remember, 100 grams is about a newton. That's if you're using G as 10. Divided by, and I'm going to go ahead and record this in meters, 0.40 meters. 2 divided by 0.40, 5. Now, take a look at my units. Nothing cancels out. I don't want anything to cancel out. K is 5 newtons per meter. Once I get that, then I plug that in here. 1/2, 5 newtons per meter times 0.40 meters squared. Let me see, 0.4 squared would be 0.16, 0.08 times 5 would be 0.4 joules. You can check my math if you want, because I do make math mistakes. Cool. More on springs in class.